Hello, good afternoon. How's everyone doing today?
Good.
Good.
Okay. All right, so we will start our discussion on complex circuits. Since previously we have discussed inductance, the mutual inductance or self-inductance of a solenoid. Now let's consider if you put a solenoid along with the circuit, what effect it will do. So in the circuit, we should have a resistor, and sometimes we have a capacitor as well as an inductor, which is a solenoid. Okay, so quickly before we go through a real circuits, I wanted to talk about the different symbols and just to sort of just remind ourselves what these represent and what kind of circuit, what kind of equations we use to describe these different symbols, circuit relations. And how does a resistance or capacitance relate to its geometry, as well as the type of field that we consider for that particular symbol. So what if I draw something like this? What is this thing? This represent, what does this represent?
Capacitor.
Yeah, capacitor. And the capacitance is proportional. The charge accumulated on the capacitor plates, right? A parallel plate capacitor will be proportional to the capacitance times voltage. Okay, that works for it looks like a parallel plate, but if you have a cylindrical shape or spherical shape, it's the same thing. Or if you take the derivative of that equation, you get the current, which is going to be C dV dt. Now, in terms of the geometry, if it were a parallel plate, right, it's going to be epsilon naught times the area over the distance between the plates. This is only for a parallel plate. And the electric field between a capacitor fields can be calculated using Gauss's law for an infinite sheet of paper. And now it's like you have two infinite sheets added together. So it's epsilon naught, epsilon over sigma over epsilon naught. This represents charge density. Okay, now sometimes we have this. What is this? This is a resistor. And voltage and current follows Ohm's law. And if you have an ohmic material, which means it's homogeneous, and a resistance is rho resistivity times the length over the area of the resistor. If it's a uniform rod with uniform resistivity. In terms of the electric field, we have the microscopic Ohm's law. E is J is sigma times E. Notice this sigma and this sigma represent different things. This one is not charge density. This is conductivity of the material. Two different things. Sometimes we have something like this. Looks like a solenoid, right? This is an inductor, which is a solenoid. V is negative L di dt. And the inductance, sometimes you can write it using the total number of rows squared times area over L, the length. Now or you can replace one of the N over L as in the number density, little n, times the big N times A. So these two are the same idea for a solenoid. And the electric field for a solenoid, right, if it's a long solenoid, is a constant, which is mu naught times number density times I. Little n represent how many turns do you wrap around per unit length. Or the flux for a solenoid is L times I, which is the current. And if we have A circuit, we often use, if you remember this from your intro physics, Kirchhoff's laws tell us the sum of a delta V around a closed loop is 0, right? Also, this is the voltage rule. The current rule says if you add up all the currents entering into a node, then all of the currents will add up to be 0 for any node, any points in the circuit. Now, of course, you have other symbols. This is representing a battery. If you have a something like this, that's AC source. So when we see these symbols, we know what they mean. Sometimes you have a something looks like this, like 2 circles together. That's a current source. So this, for example, you can have a sinusoidal source, which is changing with respect to time like this for both the current and, the current and the voltage. So current could also be something like this. So that's all our symbols. All right, now let's look at the actual circuit. So I'm going to draw, let's look at an example of an RLC circuit. Actually, let's start with a simpler one. Let's do a simple RL circuit.
Can I ask a quick question?
Yeah.
I forgot what the 2 different ends are. One of them's that turns around a solenoid in the inductor.
Yeah, N is the total number of turns. Let me highlight this. N is number of turns. Let's say you have 1,000 turns, and little n is number of turns per unit length.
Okay, got it.
Thank you. So here is my RL circuit. Once you close, okay, the switch was originally open. Once you close it off, and then you get a current running, and current is running from the positive side of the battery to the negative side, so in the clockwise direction. So what I would do using Kirchhoff's laws is going to write a voltage relationship going around the loop. So we turn on the switch. We want to be able to find the function of current with respect to time after you turn on the switch at t equals 0. So you can see that if we follow that voltage rule, right, there's a way we follow this. Okay, the sum of delta V around the closed loop being 0. So which loop that is totally up to our choice. Here you only have one loop, right? Sometimes you may have multiple loops, right? You could have something looks different. Then you have 1 loop, 2 loops, 3 loops. Then in this case, you only have 1 loop. So obviously we're just going to evaluate along this loop, right? In this direction. You can do clockwise loop or you can do a counterclockwise loop as long as you're consistent. So here I'm just going to evaluate the potential change along the loop, which is the same direction as how my current runs. So going from a clockwise direction, you can see, first of all, I'm encountering this voltage, this battery. So from the negative to the positive, I have a current raise, right? Current increase instead of current drop. So current is increased in that direction. So that's a positive V. From and then continue to go along the clockwise direction. Next, I'm encountering resistance. So along with the direction of the current, here should I have a current increase or current drop? From here to here, is this a voltage? I said it wrong. Is a voltage drop or is it a voltage increase?
Drop.
Drop, because you're going along the direction of the current. So I'm going to write negative IR because that is a voltage drop. Okay, going through the inductor. Well, that one we are just going to refer back to our formula definition here, which is L di over dt is equal to 0. So here I can solve for the current as a differential equation to find the function of I change with respect to time. So we want to solve for this. We want to be able to solve for IT. So modify this a little bit. You see that becomes IR plus, I'm gonna put the L di dt first, plus IR is equal to V. So this is actually a first order, because you differentiate, you take derivative only first order, and is a inhomogeneous differential equation, because this is not 0, this is a constant. So this is inhomogeneous. So how do we solve this? There are two methods. I'm going to go through the first method first. Differential equations are something we will need to use, but we only need to know how to solve it. It's not like we're doing a math class. So it's totally acceptable if you need to refer to your old textbook or Google an answer when you encounter differential equation, as long as we're able to solve it. So that is our purpose in this physics class. So the general method of solving this type of differential equation is, first, can we find the solution for a homogeneous version of this equation? So if we can find the general solution for the corresponding homogeneous, then we are like halfway there. So how do I make this equation homogeneous? Well, I simply get rid of the constant. So this is my homogeneous equation. We want to find the solution for that. Next, what do? We find some particular solution that is satisfied the inhomogeneous solution. So some particular solution for the full equation. So basically this original equation. Then we can add them up. Here you can totally guess. You can guess a solution, and if you plug it in and it works, your job is done. You don't have to justify how you come up with the answer, as long as that solution works. And then you would simply add the general solution from this step to the particular solution from this step, and you're getting your overall solution to the original equation ODE. But then we will probably be left up with a lot of constants. So what do you do with a lot of constants? So you will find the constants using your initial conditions. Initial conditions are something implicitly given in the physical setting of the problem. Find the constants using initial conditions. Now, for example, in this case, I want to find my current, right? The initial condition would have been something like, what is the current at t equals 0? That is something we will have to figure out using our physics knowledge. Okay, so this probably sounds very familiar to you, right? And this should not be new, because you have done some of this before. We're just again review what we learned. So let's go back to doing this method. The very first thing is, let's find a homogeneous solution. So first step is to find a general solution to the homogeneous differential equation, which is L di dt plus IR is equal to 0. Now this one we know, we can easily solve it. The I dt, if I simply just modify a little bit, divided by L on both sides, I get negative R over L times current I. Okay, and then move I all to the other side, di over I is equal to negative R over L times dt. Right, so I can integrate both sides. I integrate my left-hand side, I get the log. I integrate my right-hand side, I get negative r over times t. So this is something you're very familiar with. You get an exponential function, right? I, as a function of time, is e to the power of negative r over lt. But because of this integration, you will get a constant. So there is some kind of constant here in front of it. This is my general solution, but I have a constant, which, what is C? We have to find out that later. Okay, so that's the first step. Second step, we need to find a particular solution that satisfies the full equation. This full equation, let's rewrite it here. This is our original full equation. Is equal to V of the battery, right? This is the battery, V naught, which is some kind of constant. Okay, so here you can guess. So what might be a reasonable guess? That current is equal to what? Might satisfy this equation? Anybody would like to guess? So if I know that this solution, when I plug it into this equation, it's satisfied. It gives me 0. But I want this to be non-zero. I want this to be some kind of constant. So somewhere along the way, if I can make a constant to come up from the side, that will work, right? So how can I make a constant come up? So here would be your guess. You might guess that I'm simply just going to add a constant to my original solution, for example. Let's just say we're gonna add a constant. I don't know what that would be, but I'm gonna add a constant. And this might be a different constant than before. So here is a guess. Okay, so let's see if it works. Whether it works or not, you can go ahead and plug it in. Let's plug it in to see if this could be a solution. Okay, so let's plug it in. The first term is L times the I dt, right? You take the derivative, you get a negative R over L in front of it, and you get this e to the RLT back. That's your first term. Plus, and B, right? B is a constant, derivative is 0. Plus current, which is this entire thing, times resistance, R, this is equal to V naught, which is the voltage of the battery. So let's see if it could even work out, if it's even possible. So okay, L cancel out, I get negative, what, A, R, E, and I get positive A, R, E. This is good. This is the exponential. I don't want this, so it cancels out. And then I end up with a constant. I end up with a B times R is equal to V naught. So it looks like it is possible, right? As long as my B is V naught over R. So I have found a unique solution that satisfies my inhomogeneous differential equation. So what is my unique solution? My unique solution is I is sum A times E negative R over LT plus V naught over R. This is my unique solution. Okay, so I'm almost done. The third, what is my third step? To add them. So I will go ahead and add these two together, but I don't know these, I still have a bunch of constants. I don't know what to do, right? So I need to figure out what these constants are by using initial conditions. So here comes to figuring out what the initial conditions are. by looking at the physics, the feature of the inductors that you know how inductors behave, so we will be able to figure out what the initial conditions are. All right, so let's look at this question. If we're able to answer the current at t equals 0 right after, so 0 little plus, this means right after you close the switch. So what can we say about the current at the initial moment? So what do you think that might be? So don't think we need to discuss this. Just remind yourself of the behavior of an inductor when you have a sudden change in your circuit. What will happen? So when you can go ahead and put your thoughts in the vote in the poll. All right, let's look at your answer. Okay. So what happens right after we close the switch? Do we get a current right away?
There's an induced response.
I'm sorry, what response?
There's an induced response due to the inductor.
The inductor will respond to that change. How would it respond to that change?
There will be a potential on the opposite direction due to the IDT. The change in
yes, it will try to oppose the change. So you will not be able to have a sudden change of your current if you have inductor element in your circuit. Very good. It does not have a sudden change, which means it cannot go from 0 to non-zero in an instant. It will take time to change. So when you're talking about a very, very short time right after, so that hasn't had, which means there hasn't enough time passed by yet, you shouldn't have a significant change in your current. So therefore you should have a zero current in your circuit. Yeah, very good. So that is one initial condition. Let's use it. So we're going to use my initial conditions that current at t equals 0 should be 0. I'm going to plug in here, which means a times e to the power of 0 is 1 plus v naught over r is equal to 0. Give me 1 second. My writing was not updated in the share, so I need to share it again. Okay, so what is A constant? Constant A is negative V naught over R. Okay, so in my current, my solution is negative V naught over R e to the power of this plus V naught over R. So it becomes V naught over R 1 minus e to the power of this. So this is what I have solved for, which is a solution to the RL circuit. So what would you think that in terms of graphing it, what do you think it was best represented using one of these graphs? Okay, I'll let you go ahead and vote on this. just curious, once you enter an answer in the poll, can you change your answer by pushing something else? Like a clicker, you can change your answer, but does it work with the poll questions?
I don't think so.
Okay. Because I see someone voted for E. I know that might be a mistake because we don't have an option E here. Just wondering if they have a chance to revote if they want to. All right. Any other votes coming in? Okay. All right. So can anybody walk us through their thought process? How do we figure out which graph correctly represent the change of current over time? Oh, we do have an option E, which is none of these is correct. My apologies. I was not looking at that option here. Sorry.
Yeah, I chose E. For one, it's supposed to be a negative exponential, so it's supposed to decay, and none of these decay, but there should be a constant added to it, so it shouldn't start at the origin.
Okay, let's remind ourselves what that equation looks like. So you're saying it's a negative exponential. Indeed, it is. Yeah, okay, so as t increase, e's of negative RT over L decrease. But we have another negative sign here. So which means negative E RT over L increase, right? So as time goes on, the current will increase. And does it have the correct initial conditions? We said at t equals 0, you should have 0 current. That is the answer to the previous question. So they both have the correct initial conditions though, here, 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 and here. But we also know it should increase your current over time, right? So that sort of get rid of C only. But it's not a linear process. We know that A is not correct. So it's really just between B and D. So how do we narrow it down to which one is supposed to be?
I chose B because at B it levels off to a constant and it won't keep going up the current.
Oh yes, thank you, Jerry. That's very good. Now B shows it's going to reach a plateau, a constant, and cannot increase your current forever, right? As opposed to D, showing exponentially increasing, well, we cannot have infinity current. So yeah, so we can narrow it down to B. Very good. And so if I ask you, what do you think that final current would be? What would you say? What is this final plateau? There must be a value. Do you know this value?
V over R.
V over R, very good. And that would be the current if you, what would that look like? That would look like if you have just the battery and a resistor. So does that make sense? Does it make sense that after a long time, my circuit is no different from having a battery and a resistor? Is that consistent with your understanding of the behavior of inductor?
Yeah, I think because I think given enough time, there'll be like approximately even amount of current going through the inductors, so it's gonna not try to the backwards push is going to decrease over time because the current starts to become more constant in a sense.
Yes, very good, Cameron. So as time goes on, the inductors will only oppose the change. After a long time, you don't have the change anymore because the change only comes from when you close the switch. But it's open, but now it's closed. That is a change. But after that, there's no change. So it will not continue to oppose it and it acts just like a wire. So it would be just like a wire. And of course, the current will be what it would be just like a wire. So V naught over R. Terrific, very good. Okay, so one more question. It's asking about the delta V across the inductor. This is also an initial condition. This is an initial condition about the voltage instead of current. What can you say about the delta V across the inductor at right after you close the switch? I will let you go ahead and vote on this. So this is at the beginning, not after a long time. The previous question was about, I was talking about after a long time. This is at the beginning. Okay, any other last minute vote? Okay. All right, so kind of pretty evenly split between A and B. Yes, I agree with you in terms of initial conditions, or we say limiting cases, right? There are two limiting cases. One is right after you close the switch, and then another limiting cases would be a long time after you close the switch. And I agree with you, one of these will be 0 and one of these will be V naught. And which one? How do we decide which one is 0, which one is V naught? Any thoughts?
Well, we already figured out that the initial current is 0. So the drop across the resistor is going to be 0. And that means the drop across the inductor has to be the full voltage.
Ah, okay. So it's the initial current is 0. So the current across the resistor will be 0, which means the other drop will be V naught. Yes, very good. So the inductors, in terms of the inductors, there is one way we can quickly memorize its behavior so that it opposes the change. When you suddenly choose to close the switch, you are giving it the change. So it's opposing the change. So it's as if it's behaving like a broken circuit when at the t equals 0 seconds. So that is the beginning. However, when it doesn't have change, what would it behave like? It's like a wire, just as quickly. So E approaching infinity, like this is simply a long time after, right? So if it behaves like a broken circuit, it's as if you were using a voltmeter to measure the voltage across these two ends, right? Like it's broken. You are going to read simply the voltage across the whole thing, which is V naught, the battery. But if after a long time, then you're going to read 0 because it behaves like a wire, and the voltage drop across the wire will be 0. So here is V naught because it's at the beginning. Very good. So sometimes it's quicker to think about the behaviors of the inductors without going through the derivations of the equations. Thought that would be really useful. Okay, so what do? We have just solved for a RL circuit when V is a constant V naught. But what about you have AC current? What if you have if you have AC that is V is changing with respect to time? What about this kind of circuit? So for example, if I have V naught cosine omega t here, and I'm going to give you a RL circuit, right? So what about the time now? So this sort of our example 2. Simply switch your power source from DC to AC. Okay, we know that our method would be the same. Method 1 has 4 steps. The first step is to find the general solution to a homogeneous equation. The homogeneous equation is not changing because this is my equation now. Used to be V naught, right? Right now it is V naught cosine omega t. But my homogeneous equation is the 0. So my first step, I don't have to repeat. What I need to do is to find a unique solution I need to guess a unique solution that satisfies this full equation. So the second step needs to change. I don't have to redo my first step. So what would be a good guess?
A constant times cosine omega t plus a constant times sine omega t.
Yeah, it might also be having the sine pseudo behavior because now your power source of voltage is cosine omega t. Your current might also change with respect to time. So let's say we don't know what it is. So it might be some constant and also changing with respect to time, but it may not be always in phase with your voltage because I remember something about the inductors or capacitor kind of mess things up. So I'm going to add a phase. I don't know what these are, but that's okay. I can plug it in and find out if this is a solution. So this is my guess. It's really just a guess. I'm going to plug it in. Let's try it. Okay, plug into the left-hand side. What do we have? We have L times derivative of this. I get my A as a constant still. I'm going to get my omega, and I'm going to get a negative because it's taking derivative with respect to cosine. So I get a sine. This first term. Second term is current, A times R cosine is equal to V naught cosine omega t. So let's solve this. Okay, so I need to expand this so I can use my trig identities just to, again, there's nothing you need to memorize. You can look it up. So how does this trig identity goes? I'm looking up something plus something for a sine A cosine B plus cosine A sine B. And I have another identity for A plus B. Cosine A plus B is cosine A cosine B minus sine A sine B. So using these, I'm going to expand my left-hand side. Don't worry too much about the algebraic details. You can work it out in more detail later. But after I expand using the trig identities, I get something like this. I'm going to write my left-hand side in 2 rows. It's a little bit easier on the eye. Okay, so it's going to be 4 terms on the left-hand side, 1, 2, 3, 4, and 1 term on the right-hand side. I break it down into 2 rows because it's easier for me to match up different terms. So for example, I know it does not have a sine omega t term, right? Because the right-hand side is cosine. So all the first 2 terms has to go to 0. So I know the first row, wherever it contains sine omega t, has to go to 0. All that contains cosine omega t has to equal to the cosine term. So I get my second row of equation. Okay, so can we call it equation 1? This is equation 2. Okay, let's solve this. From equation 1, I get sine omega t cancels, right? And I get a cosine and I get a sine, which will give me a tangent phi that is negative L times omega over R. And A also cancels, you see? Okay, so that is what I've solved for phi. Phi would be reverse of a tangent of this. So, okay, so that is the phase. And then I need to solve my second equation for constant A, because I have two constants. One is the angle, one is the amplitude A. I've done one of them. I need to find the other one. To get the other one, let's cancel our cosine omega t, because it is all the terms, and rewrite equation 2. Equation 2 now becomes negative LA omega sine of phi plus AR cosine of phi is equal to V naught. Okay, you can see that, well, how do we relate this phi to the sine and cosine? We can do this, there's a trick. So if you think of a triangle, right? This is your phi, where tangent of this is negative omega L over R. So that sort of already tell you about the two sides of this triangle. And you can figure out the hypotenuse and then use it into your sine and cosine. So this is probably a trick you have already, have seen before. Okay, so from this triangle, sine of phi must be SOHCAHTOA, right? The opposed side, negative L omega over the hypotenuse. So don't worry too much algebraic details. I just wanted to be able to generally follow what I do. So you can write your cosine and your sine. And you can plug it in here. So plugging it back to this equation, you can solve for A. I'm going to go ahead and just write A here. A is going to be V naught over L squared omega squared times plus R squared. So this is my constant A, and that is my constant phi. I have found both of these constants. So my work is done, right? I found the constants, and I found the solution if my power source is AC, sinusoidal wave. So my full solution becomes, current at with changing with respect to time is A cosine omega t. No, because this phi is so hard to write, so I want to just keep my phi in my writing. I can refer people to the number of it later. I don't want to write this entire awkward thing into the cosine, so I'm going to keep it as A cosine omega t plus phi. That's the unique solution plus the general solution that we already solved previously. Again, we found A, we found phi. This is something we still yet to find, but you might think, well, that's easy. I know at t equals 0 is still going to be 0 current. Right? The behavior of inductor still remain the same. You plug in t equals 0, you get A cosine phi plus C is equal to 0. So C would be negative A cosine phi. A is already found, phi already found. So your solution is found. You can say my solution is found, but I can tell you what these constants are. I just don't want to write it out in my solution. I can tell people about these constants. All right, sorry about that, everyone. My computer had just died. I forgot that I did not have the plug on, so I'm back. Just 1 second, please. Okay, where were we? We were at the end of our derivation, right? We found our general solution when our current is a sign changing as a V naught cosine omega t. Omega, what does omega represent? It represents the frequency of the signal, right? How fast is change? So just let me, where's my solution? The solution is on this page. Okay, so let me bring another paper over. Okay, now I got some more space to write. So let me highlight the final solution we got. This is the solution we got. And all the constants are explained here. So let's see if this makes sense, right? When we get a result, we want to be able to look at limiting cases to see if have we made any mistake in our derivation. So let's see if that makes sense. If my resistor, R resistance is very large, what would that make R A? A is very small, right? Because R is on the denominator, so A is very small. Well, that makes sense because big resistors will limit your current. And if A is small, your current is small. So that makes sense. Now, if your omega is very small, approaching 0, does that make sense? Let's see if our current, now that's one limiting cases that your omega represents the frequency of your signal. If the frequency, if omega is 0, meaning that, well, it's like a DC current. There isn't really any change, right? So what would that make our solution? So IT becomes A, as in omega is 0, this just becomes V naught over R, right? Cosine phi, and what does phi become? When omega is 0, phi is 0, your phase is 0. Okay, so that goes to 1. And plus your C, and which is becoming a constant now, V naught over A. And you have a minus sign e to the negative RLT. Oh, so we have just seen this before. This is from our solution from the previous example. This is just like our DC current, a DC voltage. So they match, right? They match. So that's good. That makes sense.
Could you explain again why when omega goes to 0, phi goes to 0 as well?
V does not go to 0. Did I see phi? Oh, you say phi goes to 0?
Yeah.
Yes,
Phi.
because phi is tangent of phi is omega over R, and omega 0, this is 0. Yes. The last one is when omega is very, very fast, infinity. This means it changed super fast, right? So because what is omega? Omega is 2 pi over t, an oscillation, right? So when omega is infinity, which means the time for one oscillation is 0. So it's like super fast when it goes from here to here and here back and here. So super fast, right? So when omega is infinity, which means there's a lot of change. What happens to the current? Without looking at the solution, what would you be your guess? What was your current? What will be your current? When something is drastically changing, you have a inductor in your circuit. What would that make your current?
0.
Yeah, it's 0. And why is that?
I was kind of thinking of it as the voltage is going to push it one way, but then pull it the other way, like equally as quick. So the net result is going to be 0 current.
Yeah, here since you're changing all the time, which means your inductor will oppose that change all the time, make your current have no chance to go up from 0. So inductors really don't like changes, especially not rapid changes. So your current will be 0, and it suppress the response at high frequencies when your omega is large. And does our solution is consistent when omega is big on the denominator? A goes to 0, good. C is also minus A times something. A 0, C is also 0. So current give us 0, which is consistent. So our math match up with our physical intuition. So we have done this a little bit. Evaluation of our results, we said, good, I think we found the correct answer. All right, so that's the method 1. It's a little lengthy, but I hope it at least the process is clear. We have a clear process of going about this kind of thing. There is another method. So another method, you probably have seen this before, especially in 2530, or maybe in other class, maybe you've done this in electronics or something, is using a phasor diagram. The idea of using a phasor is really no different from treating everything as a complex exponential. So instead of treating something as cosine, you write e to the I theta. So cosine theta becomes e to the I theta. And so if your voltage is V naught cosine theta, V naught cosine omega t, you will write V naught e to the power of I omega t. And then you solve your equation that way. And your final physical quantity, what is your current? You will take the real part of your complex value. Likewise, if your voltage source is V naught sine omega t, then you solve everything, you take the imaginary part of the final result, and you get your physical, the physical value, right? What you read physically should not be imagined, it should still be real. So the complex numbers are just a way to make this a little bit simpler, the math a little bit simpler, so we can solve it. Okay, the second, I want to be able to add. Okay, so okay, good. I have still a little bit more space to write. Second method. Let's look at the second method. Is the complex number method, or it's nothing like a. Also, I can just write this complex number method. It's not really different from if using a phasor diagram. To remind us about the complex numbers, Euler's theorem, E of I theta is cosine theta plus I sine theta. So EI omega t is cosine omega t plus I sine omega t. So the general method goes like this. If your true voltage is a real part of your complex voltage, fictitious voltage that doesn't exist in real life, but right in our calculation we make that into complex circuit, and your I true current will be the real part of your fictitious current. Just take the real part of that. So let's look at our equation. This will make our equation easier to solve. So remember, this is our differential equation. If this is complex, right? This is complex. Then we can try a complex current. Let's say our current is also complex, and you can plug it in. You can see that is indeed a solution. So if I plug this back in here, I get I omega L I tilde E I omega t plus I R E I omega t equals V E I omega t. Okay, so this will simply cancel. And I'm solving for I tilde. is V tilde over R plus I omega L. R plus I omega L from here, right? So this would be my unique, like, guessed specific or unique solution to the homogeneous equation. So the final equation would be the one that I guessed plus the general solution I had for the homogeneous one, so added together. So you can see the process is quite simplified. It's pretty easy if I use complex numbers. All right, so let's see if we still have some time left. We do need to go ahead and practice a little bit and on our knowledge about complex numbers before we can do more of these type of questions. So I want to take, if I have something like this, I want to be able to take the real part of that, right? This is your fictitious currents. This is not what you physically will measure, right? Because obviously you don't measure something imaginary. So to give the final answer, I need to take a real part of this, which makes, that's why we need to do a little bit more math on how to manipulate the complex numbers. If I could get this page to move up. Okay, maybe not for now. Let's look at our quicker question. So here is a question. We are doing a little bit detour because knowing how to process the complex numbers, we will be able to use it later when we find the real part of the currents. So let's look at this. What is 1 plus I squared over 1 minus I? There's more than one method, and you can choose whichever method you want to do. These two methods are, one is multiplying it out. One is write it a numerator and denominator in a standard A times e to the I theta form. Both of these would work. So I will give you a couple minutes to discuss with others. Take a couple minutes, and then you can talk about your thoughts when you come back. Okay, so 2 breakout rooms, choose which, and it will be assigned you, give you an invitation to join. Make sure you take this picture, take a screenshot of the picture when you are trying to solve for the problem. All right, I'll come back in a couple minutes. All right, any more votes? Okay, perfect. Okay, perfect. You are on 100% agreement on the correct choice. Very good. Congratulations. So anybody would like to share their method with us? Which method did you use to get your answer?
I first turned each one into the complex exponential form,
Okay.
and then just simplified from there.
Okay, very good. Let's look at your method. So each of them 1 plus I into the complex form. This is a complex plane. Represent this on the real, this is a real axis, imaginary axis, right? So this 1 plus I is simply going to be this little dot here. That's √2. That's the magnitude. And this is 45 degrees pi over 4. And we multiplied, okay, so we square that. It becomes this. So e to the I pi over 4 squared, the power will multiply into the exponential, right? So become pi over 2. And the denominator becomes this, it's a negative. So when you combine everything together, like 2 over square root of 2, you get a square root of a 2. And pi over 2 plus, so it's going to be pi over 2 divided by negative pi over 4 is e to the I pi over 2 plus pi over 4, which is 3 pi over 4. Very good. Thank you so much, Tremor. And also, I want to show you briefly the first method. Anybody use the first method?
I did.
Okay, so what did you do? What do we mean by multiply it out? What would you multiply it by?
I multiplied it by the complex conjugate of the denominator. But yeah.
Okay.
Yeah.
All right, very good. Then expand these, and this will become 1 plus 1 is equal to 2. Okay, so if we do that method, the final result of this entire expression becomes -1 plus I. So on the complex plane, -1 plus I is this. You can see you still got a great √2 as a magnitude, but this is 135 degrees, which is 3 pi over 4, right? So you write the same result as you had here. Both of the method works. Very good. So we're going to use this method, and how we're using this to help us how to find the real current. So in the process of finding the real current, we need to know what is the true current as the real part of this. Again, you can use both of those methods to find your real current. I'm going to multiply it out using the idea of multiplying it out. So this is what we're going to do. It's going to be V naught EI omega T plus this, so multiply by R plus, R minus omega L, R minus I omega L. So this is the trick, right? We just learned this trick. Okay, so V naught is a constant, doesn't matter. I'm going to take V naught out. And the denominator becomes a real number now. So I'm going to take it out of my bracket. So that becomes R squared plus omega squared L squared. And I need a real part of EI omega T R minus I omega L. So I need the real part of this. Okay, so how do I find the real part of this? Any thoughts?
You can either distribute now and then write it in cosine sine form, or you can write it in cosine sine and then distribute.
Yeah, I could do I can use Euler's theorem to expand everything and group the real part and imaginary part together. Or I can write everything. I want to be able to write everything in the general of e to the I something format, because once I have that general format, I can just take the cosine of this to be the real part. So let us do that. Okay, so this is already in the format I want. I just need to make this into the format I want. So I need to make r minus I omega L into the general format of A, E, I, theta. You know how to do this, right? We draw a complex plane. And R is here. We do a negative omega L here. So this is represented by this dot on the complex plane. And I just need to know what is the angle theta or angle phi here. I'm just going to write phi here. Sorry, replace this with my theta just to be consistent. All right, so you can see that A is square root of r squared plus omega squared L squared, and tangent theta is negative omega L over r. Right? So this is my A, this is my theta. So this term becomes this term. R minus I omega L is equal to square root of r squared plus omega squared L squared e to the I theta, where theta is tangent, inverse of tangent negative omega L over r. So you're done. Your final solution for current is V naught over r squared plus omega squared L squared. The real part of that, the real part of this is A E I omega T E I theta. Okay, because this one is I e to the I theta, so everything together is this. So my A is the square root of this e to the I omega T plus theta. Okay, so current becomes V naught over the square root e to the I omega T plus theta. So this is still my complex current. Sorry, I need my real part, don't I? I need the real current, which is, you just simply take the cosine. Okay, cosine omega T plus theta. Where theta has already been found is tangent inverse of the tangent omega L over R. Okay, so this is your current. It looks lengthy, but it's actually easier than the previous method we have done. Remember what we did in the previous method? We did the trig identity for sines and cosines and combined group things together. So this is actually simpler, especially when you get more familiar with this. It will be much quicker in solving the problem. Okay, so this is all for today. Next week, I'll see you guys in person. We will continue our discussion on complex circuits. We'll do a little bit of practice on the complex numbers as well. All right. Oh, I wanted to do a quick update on the homework. The homework 2 was meant to be due, the complex number homework is going to be due on September 12th, not the end of this week, the week after. So you have quite a little bit of time for this. Because we always want to leave a little bit delay. So for our lecture, for your homework is some lecture we covered previously. So which means this weekend, we don't have a homework. So use the time to redo your homework, to do your homework one if you have not submitted. There are a couple of you guys have not submitted your homework. You want to be able to get the credits you want. I want you to have grades for this elective course. So now I extended the deadline for homework 1, so you can still submit it. Will be due the end of the Sunday. And I'll see you guys on Monday. Remember to bring your clickers. I will bring a couple of extra clickers just if anybody needs it. Okay. All right, bye everyone.
Thank you.
I have a couple of questions, I
Yeah,
think,
go ahead.
on the second method, because I think it is easier, especially the last part. But I guess understanding how the first part was formulated, where you sort
Yes.
of no, essentially right after we defined what V true and I true were,
Mm-hmm.
how we made the differential equation and then turned it into our guess.
Mm-hmm.
That part is kind of unclear to me.
So how we used the complex numbers. So we write our voltage using complex notation, and then we find our current, right? Is that what you were asking?
Yeah, like those steps right there are kind of.
Yeah, okay. So what was our original so okay, 1 second. So we had V naught cosine omega t as our source. So my point is, instead of writing this, we're gonna, so this is the real part of a complex number. So we're going to rewrite our V using V naught E I omega t instead of cosine omega t. So, and then find our current, which is also complex. And then we take the real part of this current will be the physical current we want to solve for. Does that make sense?
Okay. Yeah. Okay. So our original equation was V naught cosine omega t is equal to that, the differential thing, the L d I over dt plus IR.
Mm-hmm.
And then we changed the voltage into a fictitious voltage and also changed the current into a fictitious current.
Yes.
Okay. And this, okay. Okay. Yes, I'm just looking at the notes and then following along, I guess.
Yeah.
And then we changed it into this form. So then we sort of went back to what we would have found it to be for the homogeneous version of it.
Yes.
Then
So in terms of, this is complex, you can see. In terms of making the real part, I left it alone because this is already a real part. I only need to work on this part, right? That's why for the rest of this stuff, I'm only working on the first term.
okay.
But the second term is already real. Obviously, your final solution would include the second part. But I'm just working this first part separately.
Got it. Okay. So then I true was the real part of that. Okay. Okay, I think I understand after that. Okay. Okay. Yeah, I think I got it.
Okay, sounds good.
Okay, thank you.
No problem. I'll see you
Bye-bye.
on Monday on
Yeah.
campus.
See you.
Okay, bye.